This episode will focus on combinations instead of permutations. As we will see, there is a link between the two, but the key difference is that a combination disregards repetitions. Therefore, if I have the same objects in a different order, they are not counted as a separate combination, and the total number of combinations is a total number of unique elements. Some say that in combinations, order is not important. When looking at combinations, we refer to choosing k objects from a set of n, and we will see why we use this phraseology later on. First, let's look at an example, as I think this is the best way to understand the difference between a permutation and a combination. If we are looking at pairs of people, then choosing Kevin and then Duan is the same as choosing Duan and then Kevin. This second arrangement is a different permutation, but the same combination. You can see here that I am still using slots, and if we want to disregard repeats, we will need to think back to the final example in episode 1, where we formulated a way to divide out repeats of arrangements of letters. This example is good to start with, as we can list out the combinations of 2 from this group. We can see there are 6 combinations, but we need to form a way to calculate this, as it will become increasingly difficult to list our combinations when the number of objects becomes large, as well as if the number of objects we are choosing becomes large too. I'm still talking about slots because we can use the idea of permutations, but factor out repeats. We start with the calculation of 4 times 3, as there will be 4 branches for the first slot and 3 for the second. Therefore, 4 times 3 paths in total. However, this will include those types of permutations that reverse the order of people. Therefore, we need to divide out the repeats by asking ourselves how many ways are there to arrange each pair. The answer is 2 factorial, so we divide by this to give our answer of 6. Let's look at another example and try to generalize the approach. The gender of the people will come into the question later on, so don't worry about that for now. There are 4 slots, so we will begin with the calculation of 10 times 9 times 8 times 7. We now need to divide out the repeats, so again need to ask ourselves how many of the same combination will appear when we are thinking about permutations. The answer is the number of ways we can arrange the same sets of 4 people in these 4 slots. Therefore, we divide by 4 factorial. Although a similar approach, I'm going to go further and simplify the fraction by first making it more complicated. Here I have added 6 times all the way down to 1 in the numerator. To make sure there is equality, I need to do the same to the denominator, as this is how we preserve the value of a fraction. I now have a factorial on the top and a factorial on the bottom. I can also rewrite the 6 as 10 minus 4. This may seem redundant and overcomplicating it, but if we reflect on this, we can see that the answer is a fraction when all parts depend on 2 things. Firstly, the total number of people, 10, and secondly, the number of people we are choosing, 4. We can now apply this to the general case of choosing k objects from n. You can see the calculations form the same pattern. As I am choosing k objects, I need to have k terms in the numerator to match the number of slots. This will stop at multiplying down to n minus k minus 1, as we have the first term of n. Think about this for a moment as to why we don't multiply down to n minus k. We then divide by k factorial to represent the number of repeats. We can then introduce multiplying down to 1 in the numerator and denominator. And finally, we can represent the term in the denominator as n minus k. We are now left with a fraction you may have seen before, and now know where it comes from. This is known as the choose function, and is referred to as n choose k or n c k, which is how it would look on your calculator. Now we have the notation, let's look at more difficult examples. Now we have a condition that there must be 2 boys in the team. I'm going to approach this in the same way I approached the permutation question of organising students in a row. I'm going to fix the 2 boys and see how many pairs of girls I can put into the final 2 slots. The dots here refer to the fact that there will be quite a few combinations in the middle, but I don't want to just list them out. We know how many lines there will be because it is the number of pairs of girls we can choose from the 7 girls. This is 7 choose 2. Now I can change the boys, and again there will be 7 choose 2 lots of girls to go with them. I can repeat the process for the final pair of boys. There were 3 pairs of boys, so the total number of combinations of teams with 2 boys will be 3 times 7 choose 2. However, I acknowledge here that in order to count the number of situations, I have listed out the pairs of boys, but we know how to find the number of pairs of boys as we want to choose 2 boys from 3 to go with the 2 girls. Therefore, we should actually represent this as 3 choose 2 times 7 choose 2, which equals to 63. If I expand on this by increasing the numbers so I can't just list out the pairs, in this case, each set of 3 boys will have 6 choose 2 girls to go with them, leading us to this calculation. Therefore, in this example, there are 525 combinations. Now let's look at another example that is similar to a permutation example from episode 1. To solve this, like before, we can think about 2 solution paths to go down. Firstly, we can find a number of combinations with 1, 2, 3, 4, or 5 boys and then find the total. The second option is to subtract away what we don't want from the total. What we don't want, and I emphasize that I am only saying this in order to answer the question, is a team of only girls. The total number of teams will be 13 choose 5, as 13 is the total number of people and we are choosing a team of 5 from it. Therefore, we need to subtract 6 choose 5 from this, which is the number of teams with 5 girls in. So the answer will be 1,281 combinations. Notice the use of the language of at least. Watch out for this in exam questions, as it usually implies this method of subtracting what you don't want from the total should be used. And as I mentioned in the previous episode, this can apply to several different topics. I will finish with some properties of the choose function. Firstly, there are some calculations that we don't need a calculator for. 7 choose 7 will be 1 because there is only one way of choosing 7 people from 7 people, and that is choosing all of them. I will use people here as it helps to think about choosing specific things rather than just referring to them as objects. By a similar logic, 7 choose 0 is also 1, as there is only one way of choosing no people. 7 choose 1 is 7, as there are 7 individuals I can choose to get my team. 7 choose 6 is also 7, and I will explain why this is true later on. For the other calculations, we can either use a calculator or we can use the formula. You can see here there is a nice symmetry whereby we can pair up from either end, working our way to the middle. So why is 7 choose 6 the same as 7 choose 1, and so on? The answer is that there are 2 ways to think about 7 choose 1. The first is the same as we mentioned. There are 7 ways to choose one person. The second is that there will therefore be 7 ways to choose 6 people to leave out of the team and take the one person that is left. As you can see in this diagram, this is the reason why 7 choose 2 and 7 choose 5 are the same, as we can either choose a team of 2 or choose a team of 5 to leave out. This is the same for 7 choose 4 and 7 choose 3. We can generalize this as we can see the number of people we are choosing in these pairs adds up to the total number of people. Therefore, n choose k is equal to n choose n minus k. The last observation can be seen if I add in the values of 8 choose k. Again, there are some values we will know, but others we can either use the formula we found earlier in the video or just use a calculator. If I get rid of the choose notation, you should be able to see clearly that numbers on the second row are in between two numbers which sum to give their value, such as this 8 can be formed by adding the two numbers above it of 7 and 1. This is exactly how this very famous triangle, known as Pascal's triangle, is formed. In the triangle, the number 1 at the top is referred to as the 0 row. So the values for 7 choose k can be found on the 7th row, which is at the bottom of this diagram. And therefore this gives us another way to find the values on top of the formula we formed, or just relying on the calculator. I hope this episode has helped to give you an understanding of how to form the choose formula, as well as when to use it. In the next episode, I will look at permutation and combination questions mixed together in order to support further.